Hello everyone and welcome to the latest installment of the A-Level 9709 Solution Guide series. In this video we will take a closer look at paper 1.3 from the May-June exam period of 2021. So without further ado, let's get straight into it. In exercise A it is stated that a curve with the equation y equals f of x is such that its first derivative is 6x squared minus 8 over x squared. It is further given that the curve passes through the point 2, 7. We are supposed to find the equation of the curve f of x. To perform that task, we will have to integrate the equation of the first derivative of the function, and to achieve that we will firstly, using the laws of exponents provided, to rephrase the expression 8 over x squared into 8 over x to the power of negative 2. From there we can simply apply the power rules for integrations provided and can conclude that the integral of the first derivative can be expressed by the equation 2x cubed plus 8x to the power of negative 1 plus c. In the final step we will have to find c, which can be done using the information that the curve passes the point 2, 7. Therefore f of 2 equals 7. So here we just substitute x for 2 and rearrange our equation, which delivers us the result for c, which is negative 13. And in the final stage we simply put together all of the information gathered in order to describe the equation of the curve f of x. Moving on to exercise 2 of this exam paper, where it is stated that the function f is defined by f of x equals 1/3 multiplied 2x minus 1 to the power of 3/2 minus 2x, and that x is defined for all values between 1/2 and a excluded. It is further given that f is a decreasing function. We are supposed to find the maximum possible value of the constant a. Maximum possible value will serve as our signal phrase, meaning that we will have to find the first derivative of the function and equate it for 0. We can find the first derivative applying a combination of the chain rule and the power rule as provided. After having found the first derivative, we can now in step 2 equate it for 0. So in the first step we will isolate the exponential expression by adding 2 to both sides of the equation, and thereafter we can square both sides of it, and in a final step rearrange the equation for x, delivering us the result that x equals 2.5. Therefore the value for a that we have been looking for is 2.5. Moving on to exercise 3, where we are provided with a line that has the equation y equals mx minus 6, which is a tangent to the curve with the expression y equals x squared minus 4x plus 3. We are required to find the possible values of the constant m and the corresponding coordinates of the points at which the line touches the curve. In order to find the point where the tangent touches the curve, we will have to equate both of their equations with one another. So therefore we set up the following equation using the equations provided. We will then rearrange it for a quadratic function equaling 0, receiving the expression x squared minus in brackets 4 plus m multiplied x plus 9 equals 0. Since a tangent touches a curve, this means that for this quadratic equation there can only be one solution, and to make this work we will have to ensure that within the quadratic function provided the determinant delivers the result 0. So after plugging in our values for a, which is 1, b and c, into the quadratic formula, we will rearrange this entire equation for 0 and determine the values for m employing the reduced quadratic formula, which can be done since the coefficient of m squared is 1. Following through on that, we can conclude that the gradient of the tangents are either negative 10 or positive 2. Substituting those values in the equation of the line will provide us with the equation of the tangents, which are as follows. Now we will have to determine at what point the first tangent touches the curve, and to do this we will plug in the value of the gradient for the first tangent, negative 10, into the equation that we have set on the outset of this exercise. After simplification, we should be able to realize that we could reverse the formula for the whole square, take the square root on both sides of the equation and rearrange it for x, delivering us the value for the x coordinate of the touching point, which is negative 3. This value in turn we will then insert in its corresponding line equation, which will help us in finding the corresponding y coordinate, which in this case is 24, delivering us the entire coordinate for the first touching point, which is negative 3, 24. We will do the same thing in order to find the coordinate for the second touch point by again plugging in the value of the gradient of that respective tangent into the formula. At this stage we should again recognize that we can reverse the whole square formula. From there take the square root on both sides of the equation and rearrange rearrange it for x, which lets us conclude that the x coordinate of this touch point is positive 3, and this value in turn we can again plug into its corresponding line equation, which at the end lets us conclude that the coordinates of the second touch point is 3, 0. Next on to exercise 4, where in part A we are provided with the following equation, and it is further stated that k is a constant and may be expressed as follows. This means that we are supposed to show that those two fractions are identical. So since we have to transform this expression into the one below, we should attempt to find a way to express tangent x in a different way, since it does not occur in our so-called target fraction. We can make use of the trigonometric identity provided to do so. And thereafter we will try to find a common denominator for the numerator and for the denominator respectively, which in both cases is cosine x. This expression can easily be simplified, keeping in mind that a fraction divided by another fraction equals the fraction in the denominator multiplied the reciprocal. This expression can easily be simplified by keeping in mind that ignore the numerators and the denominators since they are both the same. And in a further step we simply factorize sine x in the numerator as well as in the denominator, helping us in eliminating sine x. And at this stage we can see that k can indeed be represented by the fraction 1 plus cosine x over 1 minus cosine x as well, which was to be shown. In part B of this exercise, we should hence now express cosine x in terms of k. To do that, we will simply work with this equation and rearrange it for cosine x. In step number 1, we multiply both sides of the equation with the denominator on its left-hand side. Thereafter, we expand the brackets, isolate the cosine x expressions onto one side of the equation. Thereafter factorize cosine x from both summons of the left-hand side of the equation, and then divide both sides of the equation by those brackets, letting us conclude that cosine x equals k minus 1 over k plus 1. In the final part of the exercise, we should find a solution for the equation tangent x plus sine x over tangent x minus sine x equals 4, x being able to contain the values between negative and positive pi excluded. To achieve that, we can simply follow through on the previous exercise B, since this fraction is identical to this one. Therefore, we substitute k for 4, which after rearranging this equation for cosine x equals 3 over 5. Using our pocket calculators, we will now receive two solutions, namely cosine x being either positive or negative 0.927. The reason for that is that the cosine function is symmetrical to the y-axis. We are now moving on to exercise 5, where we are provided with a diagram that shows a triangle ABC, in which angle ABC is a right angle and the length of AB 4 centimeters. Furthermore, the sector ABD is part of a circle with center A, and the area of the sector is 10 centimeters squared. In part A, we are supposed to find the angle BAD in radians, which means the angle at point A, which can be found with the help of the formula for the area of circle sectors. We already know the size of the area, which is 10 centimeters squared. And additionally, we are also provided with the radius r, which is represented by the length of AB. Substituting this equation for theta delivers us the angle in radians, which is 1.25. Moving on to part B, here we are supposed to find the perimeter of the shaded region. So in the first step, we will determine the length of the arc BD, which can be done using the formula provided. The radius and the angle are already known, so we simply plug those pieces of information into our formula, and after simplification conclude that the arc length is 5 centimeters. Next, we will find out the length of CD via AC. We know that the length of AD is also 4 centimeters, since ABC represents a circle sector. Therefore, both of those legs represent the radius of the sector and thus need to be of equal length. To find AC from there, we can make use of the fact that cosine BAC is represented by 4 over AC, and we can now rearrange it for AC, concluding that the length of AC is 4 over cosine 1.25. I've substituted BAC for 1.25 since it's what we have determined in part A of this exercise. So to find C now, we can plug in our solution for AC. meaning that the length of CD is represented by the expression 4 over cosine 1.25 minus 4. Lastly, we need to determine the length of BC, which is again done using trigonometry within this right angle. And since AB is already given, we know that the tangent of BAD, or theta as I call it here, is the same as the opposite angle divided by the adjacent angle, meaning that the tangent of this angle is represented by dividing the opposite side BC with the adjacent side of length 4. Rearranging it for B will provide us with the conclusion that BC has the length 4 tangent 1.25. To find the perimeter, we simply add up the length for the arc, that of AC and then that of BC, providing us with this entire length, which is approximately 25.7 centimeters. Moving on to exercise 6, where we are provided with two functions f and g, which are both defined within the realm of the real numbers. And in part A, it states that by first expressing each of f of x and g of x in completed square form, you're supposed to express g of x in the form f of x plus p plus q, where p and q are constants. So firstly, applying the whole square formula provided. So in the first two steps, we will, as required per the exercise, complete the square for both of the expressions of f of x and g of x. And from there, we can see that across the x-axis, the distance between those two functions consists of 3 units. Distance is calculated as the difference of two coordinates in this case, meaning here that we subtract -1 from 2, which equals +3, and that the difference between those graphs across the y-axis is again a difference, in this case 9 minus 4 equaling 5. Therefore, we have expressed g of x in a form that was required as per the exercise. In the second part of this exercise, we are supposed to fully describe the transformation, which transforms the graph of y equals f of x to the graph of y equals g of x. Therefore, the transition can be found by looking at the values for p and q, which are +3 and +5, but we need to be careful. We need to imagine what value x would have for the expression in brackets to become 0, so we have to use -3 instead. Therefore, the transition from graph f to graph g can be described by the vector -3, 5. Next on to exercise 7, where in part A we are supposed to write down the first 4 terms of the expansion in ascending powers of x of a minus x to the power of 6. This is easiest achieved with the help of Pascal's triangle and the binomial theorem as provided. Moving on to part B, where it is given that the coefficient of x squared in the following expansion of those two brackets is -20, and we're supposed to find in exact form the possible values of constant a. To achieve this, we simply need to focus on those factors from both of those expressions for which their product delivers us a coefficient in terms of x squared. In this case, 1 multiplied 15a to the power of 4x squared, and 2 over ax multiplied -20a cubed x cubed, since x cubed divided by x equals x squared. In the next step, we simply factorize x, as we are just supposed to work with the coefficients of x squared, and the sum of those coefficients is supposed to equal -20. We are simplifying this equation for as much as possible, and at this step I've decided to divide both sides of the equation by 5 for the numbers not to be larger than necessary. At this stage, applying the method provided, we will rewrite this part of the equation in order to be able to factorize the very same. So here we are able to factorize 3a squared, and for -a squared, and 4 can factorize -2, which leaves us with two expressions that are equal, and from there we will just factorize those in order to receive two factors which multiplied equal 0. For multiplication to yield the result 0, at least one of those two factors need to be 0. For the first brackets, this is done for both brackets separately, and we will receive a total of 4 solutions, namely a being either positive or negative the square root of 2 over 3, or plus or minus the square root of 2. Next on to exercise 8 of this exam paper, where two functions f and g are defined as follows. And we are supposed to solve the equation f of g of x. To make that happen, we will substitute the function of g in x of the function f and equate it for 3 as required. In the second step, we will separate the expression in brackets from the constants by adding 1 to both sides of the equation, and thereafter we can eliminate the exponent by taking the square root on both sides of the equation. From there, we will rearrange our equation for x and receive two separate solutions, namely -1 1/4 and -3/4, and as per the domain of G, whereby x needs to be less than -1/2, we can discard -1/4 as a potential solution, leaving us with x equals -3/4 being the single solution for this equation. In part B, we are required to find an expression for the inverse function of f of g. To perform that, we will substitute x for y and vice versa, and make an attempt to rearrange this equation for y. In the first step, we add 1 to both sides of the equation, and then simply swap out the numerators and denominators on both sides of the equation by taking the power of -1 on both sides of it. Next, we will take the square root and thereafter rearrange the equation for y, which then delivers us the expression for the inverse of f of g of x, which is +(-1/2) multiplied the square root of x plus 1 minus 1/2. Next, on to exercise 9, where in part A it is stated that a geometric progression is such that the second term is equal to 24% of the sum to infinity. We are supposed to find the possible values of the common ratio. To find the second term of the geometric expression, we would have to multiply the first expression with the common ratio, and it is stated that this is equal to 24% of the sum to infinity as provided. It will be our goal to rearrange this equation for r, representing the common ratio. In step 1, we will do two things at once, namely divide both sides of the equation by a and expanding the brackets in the denominator of the right-hand side of the equation. Then we will multiply both sides with the denominator and rearrange the equation for a quadratic expression. To be able to factorize this part of the equation, we will employ the method provided and rewrite the quadratic equation accordingly. Looking closely at the first two summands, we can realize that both of them contain the factor 5r, and in the latter part, both of those summands contain the factor 2. In the next step, we can factorize the brackets, which contain the same values, leaving us with the expression of 5r minus 2 multiplied 5r minus 3. Since the result of a product is 0, if at least one of the factors is 0, we will have to investigate for which values of r it is respectively the case, and for the first one it is 2/5, and for option number 2 it is 3/5. In part B, it is stated that an arithmetic progression P has first term A and common difference D. An arithmetic progression Q has the first term 2 multiplied A plus 1 and the common difference D plus 1. The following is further given. We are supposed to find the values of A and D. Since we have to figure out the values for two variables, we will have to set up two separate equations, the first one being already provided, and using cross multiplication we will get the following equation. From there we will follow through doing two things. It is stated that both P and Q are arithmetic progressions, therefore the fifth term of P and the 12th term of Q can be represented using the formula provided. Doing so allows for us to receive an equation in terms of A and D, which is desirable since it is the values for those variables that we have to discover. To set up our second equation, we will make use of the fact stated here about the sum of the first 5 terms of P and Q respectively, and we will do so by employing that very formula provided. Additionally, we will cross multiply both sides of the equation. Therefore 3 occurs as a factor on the left-hand side of the equation and 2 on the right-hand side. In the first step, we can simply eliminate the factor 5/2 and from there expand the respective brackets on both sides of the equation and bring this equation into a similar form as the first one in terms of A and D. Finally, to work out the values that we are looking for, we will have to work with a system of simultaneous equations, and in this example I've decided to rearrange both of those linear equations for A, which will enable us to find out the value for D after equating both of those expressions. 13 minus D equals 2D minus 8, and rearranging this for D delivers us its value, which is 7, and then we can substitute 7 for D in the second equation. It could also be done in the first one. It's personal preference which you would like to work with. The outcome should in both cases be the same, namely that the value of A is 6. This leads us to exercise 10, where it's stated that points A, B and C lie on the circumference of a circle with center D, and we are supposed to show that angle ABC equals 90 degrees. For that we will work with cross-vector multiplication, whereby we can easily determine whether or not this is the case. This is the case when the cross-multiplication of the vectors in question lead to the result 0. After plugging in all of our values accordingly into this formula, And performing the cross multiplication, we can simply calculate 3 multiplied 5 equals 15 and negative 3 multiplied 5 equals negative 15. Thus 15 minus 15 is 0, which was to be proven. Hence we should state the coordinates of D. Looking at the graph at the top right, we can see that D is the midpoint between A and C, which can be calculated using the formula provided, providing us with the result that the coordinates of the midpoint are 2, 4. Next on, we are supposed to find an equation of the circle. Since the coordinates of the center of that circle has just been calculated, we already know the left-hand part of the circle equation, which must be x minus 2 squared plus y minus 4 squared equals r squared, which means that we finally have to determine the length of the radius. And again, taking a quick look at our diagram, we can conclude that we can easily detect the radius by either calculating the magnitude of vector AD, vector DC, or vector BD. In this case, I opted to make use of vector BD, and employing the formula provided accordingly lets us conclude that r squared equals 17, since negative 1 squared equals 1 and 4 squared equals 16, thus 1 plus 4 equals 16, which is r squared. Furthermore, it is stated that point E lies on the circumference of the circle such that BE is a diameter. To find the coordinates of E, we will have to start from D and add vector BD to it in order to reach point E. This is the written description of our idea, so we will just plug in all of our values accordingly and receive the coordinates of point E, which is 1, 8. Additionally, we are supposed to find an equation of the tangent to the circle at E. So in order to find the gradient of the tangent through point E, we need to keep in mind that this represents nothing else but the gradient of the perpendicular of BE. But since we know that AB and BC are perpendicular to one another, this also automatically means that the gradient of the tangent through E is the same gradient as the one from vectors A to vector E, since those have to be parallel to one another, owing to the fact that angle ABC has the size of 90 degrees. Therefore, we can simply calculate the gradient for AC, which is the same as the one from the gradient going through point E, which is 1/4. What is finally left for us is to find out the y-intercept of the tangent, and for this we simply plug in everything that we know, namely we know m and we also know the coordinates of point E, which will help us in substituting x and y for the corresponding values. From here we just rearrange our equation for C and receive its value, which is 7 3/4, and putting everything together lets us conclude that the line equation for the tangent must be 1/4 x plus 7 3/4. Next on to exercise 11 of this paper, where we are provided with the following diagram that shows us part of the curve with the following equation, where k is a positive consonant. In part A, we are supposed to find the coordinates of the minimum point of the curve, providing our answer in terms of k. Our key phrase here is minimum point of the curve, which means that we have to equate the first derivative of this equation with 0. So step 1 is to identify that first derivative, which can be performed using the power rules for derivatives provided. Thereafter, we will attempt to rearrange the equation for x. In step 1, we will multiply both sides of it by 2, thus eliminating the factor 1.5. In the second step, we isolate k squared, and we can simplify the expression on the right-hand side of the equation using the appropriate laws for exponents provided. We can therefore conclude that x equals k squared being our x coordinate, and from there it's straightforward to find the corresponding by substituting k squared for x within the function, and doing so provides us with the desired y value of our minimum point, which is 2k. Therefore, our minimum is located at the coordinates k squared 2k. Next, it is stated that at the point on the curve where x equals 4k squared intersects the y-axis at P. Part B requires from us to find the y-coordinate of P in terms of k. Our signal phrase here is tangent at the point, which means that we have to determine the first derivative of our curve, which can be performed using the power rules for derivatives as provided. Please keep in mind not to attempt to find the derivative of k squared, since our argument is x and not k. In the following step, we substitute 4k squared for x in the first derivative and simplify it for as much as we can, which will deliver us the value for the gradient m, namely 3 over 16k. Now that we have found the gradient of the tangent, what is next is to discover its y-intercept. Thereafter, we will determine the y-coordinate of the point where the tangent meets the curve. To achieve that, we substitute 4k squared for x in the original curve, whereby after simplification we receive the value of 5k over 2. Since it's stated that k is a positive constant, we will only take the positive solution of the square root of 4k squared instead of the positive and the negative one, since it's not defined as per the requirements of this exercise. Since we are already aware of the values of m, y and the corresponding x coordinate of the tangent at the curve, can plug in those values in order to determine the line's y-intercept c. To perform that, we will simply go through a couple of simplifications and at the end rearrange our equation for c, delivering us the value that the tangent intercepts the y-axis at 7k4. Therefore, this is what the line of the tangent looks like. Its equation is y equals 5k over 2x plus 7k over 4. And now we can finally determine p, since it's stated that the tangent on the curve intersects the y-axis at p, which automatically means that x is 0. Therefore, after plugging 0 into the line equation of the tangent, we can see that the first summand will become 0, and therefore the y-coordinate that corresponds to it must be 7k over 4. Finally, to conclude this exam paper, it is further mentioned that the shaded region is bounded by the curve, the x-axis, and the lines x equals 9/4 k squared and x equals 4k squared. We are supposed to find the area of the shaded region in terms of k. That's the area of the region that we are required to determine. Since the boundaries are already known, we can use those to set up the boundaries of the integral for our curve, and we can integrate those summands applying the power rules for integrations as provided. Thereafter, we just plug in our boundaries for x. We can transform fractional exponents as per the rules provided. After a couple of simplifications, we should conclude that the area of the shaded region in terms of k is 49k cubed over 12. I've been your host Marco from Planet Maths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers.